All right, so here we are. This is OT, the Pirate class, and we're just going to go through Module 5 today, which is OT networking, fundamentals of networking for OT and IT networking, how they connect. And then I'll demonstrate and explain OT 110, which is currently my only DNP3 project, and it may stay that way, which I'll explain. So let me find my slides, which are here. All right. And that'll do. Okay, so we're going to talk about OT networking and some of the challenges, ways to segment the network, and other considerations as we go ahead. So your OT networking, your goal here, of course, is to have a reliable network that can withstand the harsh industrial settings. And there's LAN, WAN, field bus, and wireless networks we'll talk about. And here's the main protocols. The main one we're going to use in our hands-on project is Modbus, because Modbus has good free simulators. I only found one simulator for DNP3, and it's very limited, and we're not going to get to do much of it. And I haven't looked for or found simulators for these other ones. So the same old problem we've talked about is always here. These are legacy systems and legacy protocols, and segmenting the network and while achieving resiliency is the challenge. So LANs, of course, connect networks in a small area like within one building. WANs are larger areas. Field bus serve a specific area and connect sensors and actuators to controllers. And of course, wireless networks are more easy to set up but more subject to wireless interference. So it's a real consideration how you want to do it. One of my students is a consultant for IT, and they went to a company, and this company had a strange drug-addicted network administrator. And that network administrator set up a restaurant. He set up all the payment systems on a wireless network. And that seemed screwy. And in fact, then it was all infected with malware because they fired the guy. And what he would do is go to the bar next door and take cocaine and stay up late at night and hack the network wirelessly. So my student was hired to clean the malware off the network. He cleaned it. Next day it was all infected again. And he found out this was happening, and he called me, and I said, this is not a good use for wireless networks. I would just tear it all down and rebuild it with wired Ethernet. That's what he did, and then it stopped getting hacked. So, it's a big issue, of course. Are you going to use wireless networks? Sometimes it's the right answer, like to reach your security cameras that are high on a wall where it would be difficult to put them on wires. But often it's not because of the interference. Anyway, so Modbus is the one we're using a lot. Very common, simple, and robust. DNP3 is more reliable and used in the power industry. OPC is interoperable, and Profibus is popular in automation systems. So, you have these legacy systems. You want to arrange to segment your network to limit the lateral movement of attackers and security breaches, and you want your network to be scalable so it can grow. You can add more devices and more features without having to rebuild the existing network, and you want it to be resilient against failure of devices and interference. Wi-Fi's layer 2 issue. The pre-share key should be considered leaked. Yes, that's right. That's the authentication key for WPA. Yes, there's a whole series of attacks involving messing with the four-way handshake of WPA. Yeah. All right. So, software-defined networking. This is the future that's coming. This is where we're all headed. If you think about it these days, when you connect to a server like Google or Yahoo, you're not connecting to a physical server, really. You're connecting to a virtual server in a cloud like Amazon Cloud, and that virtual server is being served by a virtual switch and a virtual router. It's not actually going through it is, of course, passing through physical devices, but the addresses on your packets and the way routing and forwarding decisions are made are not actually tied to those physical devices anymore. You're living in virtual networks, and it's going through a virtual firewall and all that. So that's software-defined networking, where you can control exactly where all the packets go with much easier and more inexpensively than the old days when you would have to remove physical wires and install physical devices, routers and switches and firewalls to achieve that. And then we got the industrial Internet of Things. Boy, this is, if you think it's all not insecure enough yet, this is what you need. Add all the extra devices like people are putting in smart homes in your factories. Now, again, just like in your home, this will probably give you the opportunity to collect more data and control more things, but it will increase your attack surface even larger. And then there's this thing called edge computing, which is also called fog computing, where you try to move the serving function closer to the end device, so you don't have to send your data off through some big network far away to be processed. That's the idea. So you move computing near the end device where you want it. So the main challenge, of course, is legacy systems. This is coming up more and more in my consulting. There are people with devices that cannot be updated, where there are known security vulnerabilities and they cannot fix it, and so you have to put security outside it by either segmenting it from the network or limiting access through something like a VPN. Interoperability is, of course, a big issue. You have old systems speaking some old proprietary technology, and then you have normal networks out somewhere teaching things like TCP, IP, and Ethernet, and so you may have to have middleware, devices in the middle to just translate it. And network segmentation, of course, we already have this in the IT side, but you need it here elsewhere. You just break your network up into segments and have limited traffic between them to avoid malware and hacker spreading. And like I say, scalability and future proofing, you have to choose wise technologies that can expand. Don't let yourself get locked into a proprietary thing that's going to go away and then you're stuck with orphan devices. To some extent, you have that problem anyway because of your legacy system, but you want to avoid creating any more of it in the new stuff you buy. And of course, you want to have redundancy. Multiple power supplies, network paths, backups, things like combining network channels into one with LACP or Ether channels so that your network can survive failure of some of the devices. And this means you have to understand IT and OT. So network segmentation is your main control here. VLANs are been around for a long time. I think it started as a Cisco proprietary thing. It's where you label packets at layer 2 Ethernet with a VLAN tag, which is in between layer 2 and layer 3. They sometimes call it layer 2.5 of the OSI model. And now the smart switches will only, instead of forwarding traffic to every device plugged into the switch, they will only forward traffic to devices on the same virtual local area network. And now you can have a virtual local area network where all the devices, you can say, you could have multiple rooms in different buildings, and you could pick like 3 computers in this building to be part of the finance VLAN, and 3 in another, and 3 in another, and then those 9 devices are on their own virtual local area network, so broadcast traffic is restricted to those 9 devices, even though they're not physically next to each other. And the other devices plugged into the same physical switch are not receiving the broadcast traffic because they have a different VLAN tag. And this is the beginning of software-defined networking, where you're no longer tied to the physical structure of your network. You can define a virtual structure to your network, which can be different than the physical structure. So that's the idea. And therefore, to go from one VLAN to another, you go through layer 3, a router or a layer 3 switch. So that's just like they were in separate rooms with separate switches, which is the idea. So then you have subnetting. This is done at layer 3, where you take your IP addresses and group them into groups and then restrict them again and have another router routing them from one subnet to another. And you can have virtual routing and forwarding here. So instead of having to have physical hardware connect them, you have a virtual routing. It's also called another form of virtual private networks. All right, and then you can have policy-based routing. There is a problem. If you take Cisco, which I highly recommend, very interesting stuff. The Cisco classes will point out something. The internet is incredibly inefficient. The internet's routing table on the backbone now has something like 400,000 companies that are connected, each with their own IP address range. So when you send a single packet trying to connect to somebody like Google, it goes up to your ISP, and the first router has to take the address you put in and compare it and hunt through a list of 400,000 possible destinations and choose how to route it. And then the next hop has to do that again and again and again, all through the 10 or 20 hops it's going to take to get to Google. This is incredibly inefficient, and there are a bunch of ways to improve it. In the Cisco world, one thing they talk about is, I can't remember the name of it now, something like tag-based routing, where only the first packet would have to do this, and it would then assign a flow label, flow routing. It would assign a flow label to it, and then all further packets in the stream will just follow the first one with a flow label, like ants following the leading ant. And this can be like 1,000 times less processing involved for delivering packets. So that's one issue, the huge amount of completely wasted processing time and delay as you hunt through huge tables trying to find networks over and over again for every packet. And you can also have policy-based routing, which is sort of smarter than a firewall, where you decide your route based on things like source address, packet size, service type, and so on. So this is kind of like the modern layer 7 firewalls, but in the routers that are moving there. So you can balance load across multiple links, take certain traffic that's higher priority and send it through a fast path, reroute sensitive data to go through encrypted tunnels. This is the kind of reason why you want to move to this software-defined networking. You can have more complex traffic forwarding decisions made to match these situations. The access control lists are the standard, both on a single computer, on a computer network with a server, and also on routers and firewalls. You have security policies based on rules. So traffic from this device is forbidden, traffic from that device is allowed, traffic on this port is allowed, all these things. And of course, an important part of defense in-depth strategy. And modern firewalls have much more complicated access control lists than the older ones. The older ones just had IP address, port number, and direction. And now they can have much more complicated things like membership in Active Directory groups and so on. This is a big thing you're going to use a lot, is a demilitarized zone, a semi-trusted network to separate two security layers. So you have, the common case in IT is you'll have a part of your network where your public devices are, like your email server and your web server, and that will be connected to the internet with a firewall that only blocks the most obvious attack traffic. But then to get into the internal network where you have your customer data and your financial data, you have to pass through another security layer like a VPN, where you have to prove that you really are an employee of the company to get in there. So a remote access gateway is one way to do it. And this is, of course, a common issue. You want to force all traffic from the OT network going to the internet to be heavily restricted and limited. So web servers, this is what I was talking about. You put your web server in the DMZ, so if your web server gets hacked, which is very likely because it's constantly taking requests from all these people on the internet, and there are vulnerabilities that appear in your web server software and such, then they would only have access to your less critical stuff in the DMZ. They'd have another barrier to limit them getting into your higher security stuff, like the OT network. And you can have multi-tier structure. You can have one DMZ for external facing services and a second one for internal services. So you pass through several layers of security and inspection going in and out. And the point of this is to isolate threats and impede lateral movement. If you look at the attack model from MITRE, which is the modern standard to organize your thinking about security and intruders, it's a big deal to limit lateral movement. People can almost always get on a device. This is almost impossible to stop. You get somebody to open an email attachment or something, then they're on one device, but their next task is to somehow move through your network, taking over more and more devices, and you impede lateral movement with your segmentation. So software-defined network has a system that controls the network and then another system that forwards the traffic. And when I took my Juniper certification class, they explained this. It was really quite interesting. The control plane runs at a totally different speed than the data plane, just like you'd think. Your control plane might not be able to handle, 1 terabit of packets per second, but it's just setting the rules, and then there's a data plane below it that is forwarding the packets, just subjecting them to really quick inspection controlled by the control plane. So the control plane doesn't have to respond to every packet. It sets a rule, which is something simple, like a simple regular expression or something, which applies to all the data streaming through. So you can have a centralized network controller, and then you can have dynamic network configurations and enhanced segmentation. You can make rapid changes to your network configuration, if necessary, perhaps responding to a burst of traffic by doing something like limiting the traffic or turning on some other device to handle the traffic. And you can adjust your network segmentation as necessary, which you will often have to do during incident response. You want to segment some network or limit the traffic partially in one part of the network while not affecting the other parts that you still think are clean. So that's software-defined network. It's more easily scalable, of course, than having to buy new hardware to make your network bigger. And you can have better network monitoring and better implementation of security policies as you detect things. All right, so air gaps are physically separating networks. No network interface connected to the other systems. So one option here is a safety instrumented system in an ICS. The point of this is to detect dangerous conditions and return the system back to a safe state. And this is often air gapped, so it's not connected to the internet at all. So you can trust your safety instrumented system to take you back to a known good condition. Physical segmentation, of course. You either don't connect things at all or you put a physical device in to separate them, like a firewall that will limit the traffic that moves from one side to the other side. All right. Another issue, of course, is you want diversity in your equipment. The same thing's true of any large network. For example, the DNS backbone. You want to have devices from different vendors because one vendor may have a security flaw and all those devices are vulnerable. And if you have devices from other vendors, then of course you avoided a single point of failure. All right, so you need duplicate components, duplicate power supplies, routers, switches, Ethernet links, internet links, I mean. You can combine several links together into one logical link with LACP. Therefore, for example, if you pay for two ISPs, which is a commonly recommended solution, so you have Comcast and AT&T, then if you're only using one of them until the other one fails, you're wasting your money most of the time. So most of the time you would combine the two channels into one that would be faster. And then if one fails, it slows down, but you're getting the benefit of both of them most of the time. Ether channels is another way to do it. And spanning tree protocol is necessary in all complex networks because if you have multiple wires, like two Ethernet wires going from one device to another, then you can have a loop where traffic goes around and around in a loop forever. And spanning tree protocol prevents this by detecting loops and deliberately turning off some of the connections so there is only one path out, and it only turns on the other connection when one fails. So that's important. Otherwise, your network could freeze up from packets going around in circles. One problem, remember, from your Net Plus is at layer 2, Ethernet does not have a hop count. At layer 3, IP has a hop count, so if a packet makes more than a certain number of hops, typically 30, it will just be thrown away. But Ethernet does not have that. You can get a storm in Ethernet where packets go back and forth forever, flooding the wire with unnecessary traffic, and you prevent that with spanning tree protocol. That's multi-WAN. Yeah, LACP and Ether channels are the same idea, but different protocols. Yes, absolutely. Good. And you're right. LACP and Ether channels are, I think, both at layer 2, but I'm not quite sure. You're right. What I was describing is multi-WAN when you go to the internet. Thank you. I appreciate the correction. Right. And then there's something called virtual router redundancy protocol that will let you combine several physical routers into one effective virtual router. I've never used that, but it sounds like a good idea. All right. So scalability is the ability to gracefully handle expansion. Flexibility is your capacity to implement new features, system upgrades, new emerging technology, and of course, if your design is modular, that improves both of these so you can just buy more components and plug them in, having them work smoothly with the existing components. That would be nice. And one thing you often do is use virtual machines or containers, which are really just a faster, kind of smaller kind of virtual machine. This is a big issue. I went to a VMware conference, and they had a guy there talking about a huge company where they had all these servers. And the problem is, for the server cluster to work really well, the servers had to all be the same. So after a few years, their servers started breaking and they were out of date. So they had a whole closet full of the old broken servers, and they were constantly cannibalizing the old ones to find another one of these old NICs to match the other NICs. And they said, this is really getting expensive. And they wanted to upgrade to new servers, but the new servers wouldn't interact well with the old servers. And they said when they switched them all to virtual servers, that solved that problem. Now they have old and new server hardware all running identical virtual machines, which make a virtual cluster where everything is exactly the same NIC at exactly the same patch level of everything, and therefore the virtual network works well, and they can now replace the old hardware with new hardware as much as they like without actually affecting the virtual network. So that's one of the many advantages of virtualization. And like I mentioned, edge and fog computing are these ideas that locate computing closer to end devices so you don't have to send things far away to be processed. And of course, the cloud is big for IT, although I think not so much directly for OT, because the whole point of OT is you have to connect to physical devices you're dealing with. But of course, almost everybody's putting everything in the cloud now on Amazon or Google Cloud or Oracle Cloud. So it's very easy to just purchase more resources. You don't have to bother buying hardware and arranging for power and backup and all that. All right, let's try a Kahoot. This is chapter 5, and I've got it here. Clean up my screen a little, and here it is. Good. It's nice to have more than 3, so there's some actual competition. All right. All right. So what protocol gives you fast communication in automation systems? That's what Profibus supposedly does. And I wish I had more details about it or hands-on projects. So far, I've not found a way to make one for Profibus, but maybe I'll be able to work that out. Anyway. All right, which one gives you unprecedented control over network traffic? Yeah, software-defined networking. Good. And which one limits the reach of broadcasts? All right, that's VLANs. That's what they do. All right. All right. All right, good. Stop the recording.